about the examples of division of sign magnitude numbers in computer architecture. This algorithm is used in computer architecture. So first of all, let us see what the algorithm says. So here at the top, we have the divide operation. For division, we have two numbers. The first number is stored in AQ and the divisor is stored in B. Then first of all, we check whether there is some overflow. For checking the overflow, we take QS as the sign of AS and BS. So we take XOR of AS and BS, where AS and BS store the sign of the two dividend and divisor. And the SC is uh, given as n minus 1 because here it is for sign magnitude numbers. But for division, we do not use the bit which is used for sign. So the total number of bits including sign is n, but here we are using n minus 1 bits. That means bits, the number of bits without sign. Now, first of all, we compute a plus b complement plus 1. And if there is some value in e, if e is equal to 1, then we have a divide overflow. And if the value of e is 0, then we do not have the divide overflow. So if there is no divide overflow, that means a is less than b. And then we follow this side of the algorithm. So if there is no divide overflow, then what we do, we first of all perform shift left of the three variables E, A and Q, where E is the uh, bit of the accumulator where we store the overflow or where we store it is called an extended accumulator bit, and in A and Q we store the number. So now if after performing the shift left, if there is E is equal to 0 or E is equal to 1, depending upon that, we follow the path. So if E is equal to 1, what do? We perform A plus B complement plus 1 and then make the value of Qn as 1 and decrement the sequence counter. When we follow this path, that shows that A is greater than B. But this A is greater than B is after shifting left. So we should not get it confused with the A is greater than B, where we have not yet performed the shift left. And we have only computed this A plus B complement plus 1. And there we get the E, then this A is greater than B. Then it is divide overflow. But after performing shift left, we then once again compute A plus B complement plus 1. And if after performing shift left, if E is equal to 1, then we compute all this. And if the value of E is 0, so whether the value of E is 0 or 1, we definitely perform E is equal to A minus B. That is, we perform A plus B complement plus 1 in both the cases at the first time after performing the shift left. Now, if after performing the shift left, and if the value of E is 0, and once again when we compute A plus B complement plus 1, and there we get value of E is equal to 1, then that means second time we are getting E is equal to 1. Then this shows that A is greater than or equal to B. But if after performing shift left and then performing A plus B complement plus 1, if the value of E is 0, then this shows that A is less than B. And in that case, what we do, we simply add A and B and we do not make any changes to the Qn, the last bit of Q, and then we decrement the sequence counter. If the value of sequence counter is not equal to 0, we once again repeat this cycle again and again until the value of sequence counter becomes 0. Now let us understand this algorithm with the help of an example. So first of all, suppose we have to perform 22 by 7. So this is our quotient, this is our dividend, and this is our divisor. So first of all, we write the binary code of the dividend and the divisor. So binary code of 22 is 10110, and for 7 it is 111. Now since both the numbers are positive, so sign of A is 0, sign of B is 0. And what do is, now here we can see that the number of bits, because we almost always require B complement plus 1, as we had seen in the example, B complement plus 1 is most of the time it is required. So we compute it previously. Now what we do, we check the number of bits in the divisor. So here you see the number of bits in the divisor is 3. That means the 3 bit of the register we will be using. So as there are 3 bits in B, and as you know, we have not included sign bit in representing 7 as 111. So here we can say that n minus 1 is equal to 3, because here if we include the sign bit, then the number of bits is n, but here because we have not included sign bit, so as was in the algorithm, what do? We use n minus 1. SC is initialized by n minus 1, so here n minus 1 is equals to 3. Now what we do is, this is the important step, convert A into double this number, that is 6 bits. So earlier we see in that while representing A as binary, we have only 5 bits. So we have to double this number. So then that means we can add extra 0 to the left and store it in A queue. So we have stored one more extra 0 at this location. And now this is this. Now why we have added extra 0? Because the number of bits in 7 were 3. So we have to make 6 bits. So for having 6 bits, 1 0 extra has been added. Now we divide the number of bits into two different parts. One part containing 0 1 0 and the other part containing 1 1 0. And then what do? We store the first 3 numbers, first 3 digits into A and the last 3 digits 1 1 0 into Q. So these 3 bits 1 1 0 are stored as Q. Now before performing division, first we will check overflow. And for overflow, what was the condition? The condition was that EA is equal to A plus B complement plus 1. So we have completed this. We have stored the dividend in AQ and divisor in B. We have computed the sign. We have computed SC is equal to N minus 1, which was 3 in our case. Now we compute EA is equal to A plus B complement plus 1 to check whether there is an overflow. So if E is equal to 1, then there is overflow as shown here. And if E is equal to 0, there is no overflow. So we check EA is equal to A plus B complement plus 1. A is 0, 1, 0, and we have already computed B complement plus 1, which is equal to 0, 0, 1. When I add these numbers, the output is 0, 1, 1. That means E is equal to 0. And as per our algorithm, when E is equal to 0, A is less than B and no overflow. So before performing division, what do we require? We should compute whether there is some overflow or not. If there is overflow, we will stop. And if there is no overflow, we will start performing the division. So for performing the division, I have made a table which is consisting of different columns containing operation E, A, Q, and SC, which is equal to N minus 1. Now, as we had computed that SC is equal to N minus 1 and N minus 1 was computed as 3. So I write it as 3. What is A? A is this 3-digit number. And what is Q? Q is these 3 digits number. And what is E? We initialize E with 0. Okay. So initially we initialize E with 0. A is we have computed, Q is we have computed, and SC is the number of bits in the second number, that is dividend, so which is equal to 3. Now, first of all, according to the algorithm, what do? We perform the shift left, and then compute the value of E. Depending upon the value of E, we proceed further. So let us first compute shift left and find what is the value of E. So when we perform shift left, this 0 is moved here. This 1 is moved to this place, and we add an extra 0 here. So this is shift left. After performing shift left, we find that E is equal to 0. So either after performing shift left, either E is equal to 0 or E is equal to 1. What do? We add 2's complement to A. So as for algorithm, we are adding, because either E is 0 or 1, we add 2's complement of B to A and then check whether if E is equal to 1 or 0. So because E was equal to 0, so we will proceed this path. Now this path may go downwards or this may also go this right, depending upon the value of E, which will be computed after performing A plus B complement plus 1. So here we compute A plus B complement plus 1. So we see that no extra bit is generated over here. So our value of E is 0. So if the value of E is 0, we don't proceed right, but we only move downwards. And in the downwards, what do? We add A. That means E is equal to 0. So here what do? We add A and B and decrement the value of counter. So here we have added the value of A and B. So our A was now 110. And B is, as we have computed already, this is 111. So we add 110, this 110, which is the present A, and 111 to find the sum. Here, after adding these two numbers, we find that there is a carry. So what do? We discard this carry because this carry of sum computation at this point of time is of no use. So this is, and also what do? We decrement the sequence counter. So from 3, it becomes 2. So we have completed one cycle. We have decremented the sequence counter, but still SC is not equal to 0. We once again proceed further to perform shift left and check the value of E. So when we perform shift left, here we have performed shift left. So this one was discarded. So this one is moved to here, and this 0, 1 is copied, and then this one which was there in Q is moved here. Here two zeros are remaining, and we add one extra 0 to Q. After performing shift left, we find that E is equal to 1. That means we proceed towards the right path. And in the right path, what we do, whether E is equal to 0 or 1 after shift left, we definitely have to add A plus B complement plus 1. So this is our A, and this is our B complement plus 1. So we add these two numbers, and the output is 100, 100. And then what do? After adding, we initialize Qn is equal to 1 and Sc is equal to Sc, decrement the value of Sc. So we have performed this task. Then if if E is initially 1, then what do we confirm? That A is greater than B, and we make Qn is equal to 1 and decrement the value of counter. So here the value of Qn is made 1. So here this 0 was converted to 1, and the value of counter 2 was decremented to 1. So once another cycle of this division operation is completed, once again we move to the top and perform the shift left. After performing shift left, this one is moved here, these two zeros, and this 0 is moved here. This 0, 1 remains here, and we have added extra 0. Once again, because we have received the value of A, E is equal to 1, that means A is greater than B. And what do we have to perform? We have to compute A plus B complement plus 1, make Qn is equal to 0, and decrement the sequence counter as we had done previously. So here this is B complement plus 1 as we had computed previously. This is our B complement plus 1, which is 001. So we add these two numbers, make the value of Qn. This 0 is converted to 1, and we have decremented sequence counter from 1 to 0. Now, because our loop stops when the division operation encounters the sequence counter to be 0. So now we have encountered sequence counter to be 0. So our result is at in the variable Q and A. So in A we have the remainder, and in Q we have the quotient. So what is our Q? Our Q is 11011 means Q is 3. And what is R? R is 1. So what was our question? Our question was 22 by 7. So when we divide 22, we get the quotient as 3 and remainder as 1. So this is our remainder, which is equal to 1. And what is the sign of Q? Sign of Q is AS XOR BS. So both the numbers were positive. So the sign of the quotient, and that means this quotient is positive. So we can write 0011 with the sign as Q. So our answer is 0011. Here, this Q shows the sign bit. Now let us take one more example of a negative number and a positive number. So here our dividend is minus 29 and 10 is our divisor. So here we find that sign of first number is positive, negative, and the sign of the other number divisor is positive. So AS is equal to 1 and BS is equal to 0. A is equal to 29. So this is our 29. B is equal to 10. So we find the here the numbers A and B are taken as 29 and 10. We do not take this negative number for the division operation because the sign is used only in the question part, and the remaining dividend and divisor have no changes. So this representation of 29 in binary is equal to this. Representation of 10 divisor in binary is 1010. We require B complement plus 1 as we had seen in the previous example. So we have already computed this. Now in B, we have how many digits? We have 4 digits, and these 4 digits are without sign. So as we had seen that the sequence counter value n minus 1 is equal to 4, because here we are not using the sign bit. So when we are not using the sign bit, we can see that the number of digits here is 4. So n minus 1 is equal to 4. So as there are 4 bits in D, so what do we want? We want that this A should be converted into twice the number of bits of B. So here we have 5 bits. That means we have to add separate 3 bits at the left so that the number of bits in A and Q remain the same. So now if I divide this number into 2 parts, so this part will become A and this part will become Q. And the number of bits in both the parts A and Q is equal to the number of bits in B, which is equal to 4. So now here when we compute, first of all, before computing division, what do we find? We first find whether there is some overflow. For overflow, what do? We compute EA is equal to A plus B complement plus 1 as was seen in our example. So here we compute A plus B complement plus 1 and depending upon the value of E, if E is equal to 0, then there is no overflow and we will perform the division operation. So now what do we will do? We will just compute this EA is equal to A plus B complement plus 1. So this is our present A, this is A, so 0001. And what is our B? B is 1010. So we add, sorry, we require B complement plus 1. So this is 0110. So I have added 0110. And when I add these two numbers, the output is, I think I made some mistake. This is 1. Okay. Okay. So the output is 0111. So here once again we received E is equal to 0. This means A is less than B, and if A is less than B, as we have checked previously, there is no overflow. So now we can proceed with the division operation. So first of all, we initialize E, A, and Q and SC as seen previously. We initialize E with 0. What is A? A is 0001. What is Q? Q is 1101. So here, and sequence counter is n minus 1. This is equal to 4. So first of all, as we had seen previously, first we perform shift left. When we perform shift left, so this 0 is moved here. Then what is remaining? 001. And this 1 from Q is shifted to left. Then here what is remaining? 101. And we add an extra 0 at the end. Now since here we get the E is equal to 0. So after shifting whether E is equal to 0 or 1, we first of all, we perform E is equal to A plus B complement plus 1. So what is our A? This is our present A. And what is B complement plus 1? This is 0110. So I add these two numbers. So since no extra digit is encountered, so E is equal to 0. And as seen previously, if E is equal to 0, once again, after performing A plus B complement plus 1, this definitely shows that A is less than B. And if A is less than B, what we had done previously, we have added A and B and decremented the sequence counter as shown in our algorithm. This E is equal to 0. So what do? We add and then decrement the sequence counter and perform the same operations again and again. So here, after adding once again, because here E was 0, here E is 0. So I add the two numbers and decrement the sequence counter. Now for the next step, because here I received an extra bit for E, but this B is of no importance to us because this we have received after computing the next step. EA is equal to, if E is equal to 1 at this step, then that is of our decision making purpose. But after performing this A plus B, if E is equal to 1, then we have to discard this bit. So we have discarded this bit also. Now, once again, one cycle is over. So once again, we perform the shift left operation. So what do? We shift this 0 to here. Then the remaining is 0111. And then this one of Q is then shifted here. What is remaining here? 010. So the 010 is there. And because of shift left, I have added one extra 0 to this place. Once again, I have received E is equal to 0. And if E is equal to 0, what do? We perform A plus B complement plus 1. What is our present A? Our present A is this. What is B complement plus 1? B complement plus 1 is 0110. So I add these two numbers. Once again, the output is 1101. No extra digit E is received. That means E is equal to 0. And as computed previously, if once again, after computing this, If we get E is equal to 0, that shows A is less than B. And what do? We add A and B and decrement the sequence counter. So we add A and B. If at this point we get an extra bit, we discard this bit and we decrement the sequence counter. So this sequence counter is decremented from 3 to 2. Once again, the another cycle is completed. We move to the third cycle, and in the third cycle, we once again perform shift left EAQ. So this was a number 0 triple 1. So this 0 is shifted to this place. Then what is remaining? Triple 1, this triple 1, and from here, this 0, because we are performing shift left, everything E, A, and Q. So this 0 is shifted to this particular place. What is remaining here? 100, and we add an extra 0 at the end after performing shift. Once again, we find that E is equal to 0. After shift left, if E is equal to 0, we again add A plus B complement plus 1. Now, what is A? This is our A. And what is B complement plus 1? This is equal to 0, 0. So I add the two numbers. Here, once again, I get an extra bit, but at this point of time, this extra bit is of importance, because here, when have we received E as A1 after performing EA is equal to A plus B complement plus 1. So at this point of, if E is equal to 1, that means A is greater than B. And then here we don't discard it, but we use Qn is equal to 1 and Sc is equal to Sc minus 1. So here, because we have received this E is equal to 1, that means our A is greater than B. So what do? We make changes to the sequence counter and make Qn is equal to 1. So this 0 was made to 1, and we have decremented this sequence counter from 2 to 1. Now, once again, this third cycle is also completed. Once again, we perform shift left. After performing shift left, this 0 is moved here, 100 is from here, and this 1 is shifted to the A part. So this 1 is shifted. What is here remaining? 001. This is 001, and I have added one extra 0 at the end, because in shift left we can add an extra 0. After performing shift left, what do? Always we check whether E is equal to 0. So here we find that E is equal to 0. So when E is equal to 0, once again we add A and B complement plus 1. So this is our present A, and this is our present A, and what is B complement plus 1? This is B complement plus 1. We add both these numbers, and we get four ones. So no extra digit. That means once again, we do not move towards the right, we proceed to the left path. And in the left path, what do? If A is less than B, what we do? We simply add the two numbers and decrement the sequence counter. So our first number is these four ones, and the second number is B, and B is here, how much? 1010. So this is our B. So we add the two numbers, we get a carry, this is 1. But here, after performing this 1 is of no use, so we discard this one. Then we decrement the value of sequence counter. So this sequence counter is made from 1 to 0. Now, because the sequence counter is now 0, so our cycle stops, and this is our Q part, and this is our remainder part. So how much is the remainder? 1001 is the remainder. So this remainder is equal to 9. And how much this is Q? Q is 10. So this is equal to 2. So quotient is 2 and the remainder is 9. The sign of quotient is AS XOR BS. That means QS is equal to 1. So that means our final number Q is equal to minus 2, or we can, if we want to add the sign, then Q is equal to 10010, where the starting bit 1 shows the sign. So this is minus. Thanks for watching the video.